This video focuses on solution composition, specifically molarity, using molarity as a way of expressing the concentration of a solution in units of moles per liter. You'll see molarity symbolized as that big capital M. There should be nothing in this video that you've never seen before. This should be all review, but it's a good review, and it's something that we're going to use all year long. You're going to see molarity in, nearly every chapter. Before we get into any calculations with molarity, we should just remember what it means to form a solution. And as an easy example, we could look at sodium chloride. I think we had sodium chloride in a previous video. When sodium chloride is aqueous, in solution, that really means that the ions have separated or dissociated. So we'd have +1 sodium ions swimming around in the water. They're covered with those little water molecules. They're shells of hydration, so they're very stable. There's also chlorine ions swimming around in the water with their little shells of hydration. Dissolving a compound in water is a physical change. If I evaporate the water, then I lose those little shells of hydration, and the two ions are attracted to each other, and I go back to the original solid phase. Don't get dissociation mixed up with decomposition. We're not decomposing the sodium chloride when we make a solution. In a decomposition, you have a chemical change. Then I'd have sodium metal and chlorine gas, and that's not what happens when I form salt water. That would not be something I'd want to gargle, like little chunks of sodium metal and toxic chlorine gas, and that could be kind of messy. So there's a big difference between dissociation and decomposition. We're only talking about dissociating the ions when we form a solution. So for example, if I had a 1 molar sodium chloride solution, I'd have 1 mole of sodium chloride dissolved in about 1 liter of water, enough water to make 1 liter of solution. Now, if I wanted to, I could look at the periodic table and add up the mass of sodium and chlorine, and then I could get the exact amount in grams that I would dissolve. So if sodium has a molar mass of about 23 grams and chlorine's a little over 35 or so, I'd be looking at like 58 grams dissolved in about 1 liter of water. Enough water to make 1 liter of solution. If I wanted to do some calculations with molarity, there's all kinds of ways that we can kind of manipulate this little moles per liter equation. What if I had something like this guy? Calculate the molarity of a solution prepared by dissolving 11.5 grams of sodium hydroxide in enough water to make 500 milliliters of solution. Molarity is moles per liter, but this is pretty common that if we're in the lab, we're not measuring in moles, we've measured our solute in grams. So first thing I'd need to do is change that 11.5 grams of sodium hydroxide. That should be the correct formula. Yep. I need to switch this out of grams into moles. 1 mole of sodium hydroxide. I just find the molar mass on the periodic table. And again, we kind of mentioned before, when you use the periodic table, especially if you're using that one that's given in the like the little AP packet, the molar masses are reasonable. Don't round them. Even if you get something that's really close to a whole number, I know you're really tempted to round, I would leave the decimal spots that are given on the periodic table. Now, sometimes they really do come out to be whole numbers. In this case, I'm going to say it's about 39.99. And depending on what periodic table you use, you might have exactly 40 grams, and that would be okay. But don't round it to 40. If you're using a periodic table and it does give you 0.99, just leave it. We'll round at the end. So now I plug this in my calculator, and I will round it to 3 sig figs. I'll leave the amount given in the original measurement, which is the 11.5. So now I'll leave this as 0.288. moles of sodium hydroxide. All right, we're ready to roll here. Molarity is moles, 0.288 moles per liter. And again, this is pretty common. Often when we make solutions, we don't need a full liter, so we may have an amount in milliliters. And yes, it needs to be changed to liters. So this would go in as 0.5. And now this bothers me. In the problem, it's just listed as 500 with no decimal spot. Grr. So I don't know. I don't really want to leave one sig fig in my final measurement. So if it's okay with you, I'm just going to add a decimal spot in there. And I'm going to pretend that it was exact. We made exactly 500 milliliters of solution. Because I don't want to leave this as one sig fig. So down here, let's go 0.500 liters. There we go. All we do now is plug in our calculator. We'll leave 3 sig figs. 0.576 molar. And that was the sodium hydroxide. Does that ring a bell? I'm hoping it does. This is a really common type of calculation that we'll use. And we can manipulate this equation in so many different ways. We may be solving for the molarity. We may be solving for moles. Or we may be solving for a volume. This is a handy little equation. You'll want to use this one quite often. This next one, I like this question too, because this kind of gets at the heart of what a solution is. Give the concentration of each ion in the following solutions. We'll just look at this cobalt nitrate solution. I need the formula for cobalt nitrate. Cobalt 2 nitrate. So this is cobalt plus 2. Nitrate is minus 1. So I've got some cobalt. I need 2 nitrates. This is a 0.5 molar solution. So it's aqueous. It's in solution. There we go. When this thing is in solution, all the ions dissociate. They split apart from each other. So I'm going to have a cobalt ion, which is plus 2. That guy's swimming around. And now there are 2 ways that you could write this. Most of us would say 2 nitrate, negative 1 ions, aqueous. By putting the 2 in front, we mean that there are 2 individual nitrate ions. And that's what happens in solution. In the original cobalt nitrate molecule, there are 3 ions. There's a cobalt and 2 nitrate ions. In solution, they all separate. So I have 3 individual ions swimming around in the solution. Now, if that confuses you, you can kind of think of it as being like nitrate and nitrate. There are 3 ions. There's 1 cobalt and 2 nitrate ions. Now, if we were to do this, this would be bad. Don't do this. Sometimes people will write it like NO3. They'll kind of do something funky like this because they'll be like, I don't know, let's just split apart the original molecule. Ooh, this one's bad. That's a bad one. Sad face. By putting this 2 at the bottom, like outside the parentheses, that makes it seem as if those 2 nitrates are somehow bonded together. And that's not what happens in solution. In the original molecule, yes, there's a cobalt and 2 nitrate ions all bonded together, but not in solution. Those 2 nitrates are separate. So your 2 options of noting that would either be to show 2 separate nitrate ions, or most of us would put the 2 out in front. And that shows 2 individual nitrates, not a little subscript 2 like in the compound. Okay, so I have a 0.5 molar solution of this cobalt nitrate. When it dissociates, everybody splits. So since there's 1 cobalt ion per cobalt nitrate molecule, I should have there we go, 5 moles of cobalt ions per liter of solution. I get 1 cobalt ion for every 1 mole of cobalt nitrate. I have half a mole. I'll have half a mole of cobalt ions. The cobalt nitrate molecule has 2 nitrate ions, so when they dissociate, I should have 1 mole of nitrate ions per liter of solution. That's important because we'll eventually do some stoichiometry, and they might ask us, like, what is the concentration of a remaining ion after the reaction occurs or something like that. So we may need to look at the original molecule to say, okay, well, how many moles of nitrate will be formed for each mole of cobalt nitrate? Ooh, there's 2. So if I started with half a mole of cobalt nitrate, I double that. I should have 1 full mole of nitrate ions. I like that. I don't have to do a funky calculation, but it does get at the heart of what's happening when something forms a solution. So does this one. I like this little zinc chloride question. How many moles of chlorine ions are in 1.75 liters of a 1.0 times 10 to the negative third molar zinc 2 chloride solution? That's not very concentrated, is it? All right, so let's see what we got here. Let's start with the molarity. 1.0 times 10 to the negative third molar. Zinc is +2. Chlorine is -1. I need 2 chlorines. Molarity is moles per liter. I have 1.75 liters. Well, that's not so bad. I can cross multiply and solve this sucker for moles. 0.00175 moles of zinc chloride. All right, so now just kind of like the last one, in a dissociation, this zinc chloride will split into all its individual ions. So I'll have 1 zinc ion, that's +2. I will have 2 chlorine ions. Best way to write that is probably like this. Here's dissociation. I like that. Not to be confused with decomposition. So don't do this. Although this is often like a wrong answer if this were multiple choice. Pick the equation that shows the dissociation of zinc chloride. I'd bet you money that this would be down as one of the wrong answers. And it's probably one of the wrong answers that gets picked a lot. Zinc and chlorine. That's a decomposition. That's a chemical change. If I wanted to put phase symbols in, like originally zinc chloride is a little white crystalline solid. If I decompose it, I'd get zinc metal. That's a solid. And toxic chlorine gas. That is not what I want to do when I just form a solution. I'm going to take that zinc chloride, I'm going to put it in water to make a solution. And as it dissolves, these ions dissociate. So when I put aqueous, I mean that they're in solution. They're surrounded by their little shells of water molecules. So this is sad face. It's a fun reaction. But it's not what we're talking about here when we're just making a solution. So in this solution, I started with 0.00175 moles of that zinc chloride. When it dissociates, I'm going to get 1 mole of zinc per mole of zinc chloride. So this would be a 1-to-1 ratio. Moles, that's a weird looking 7. I can do better. 7. And then I get twice as much chlorine. So all we have to do is double it. 0.00350. There we go. We just look at the ratios in the equation. For every 1 mole of zinc chloride, I should get twice as many chlorine ions. And that should answer the question, how many moles of chlorine ions? There we go, 0.0035. The last little thing that I want to look at in terms of molarity is describing how to form a solution. And you'll be doing this quite a bit in the lab throughout the year, and sometimes people kind of just take it for granted. And eventually it should be something that comes very easy to us. You know, we can go in the lab and measure our grams and throw it in some water. Boom, we have a solution. It is a question that's popped up on the AP test quite a bit, where they'll say, you have the following equipment available in the lab. Explain how to prepare this solution. And that might be like part one of a multi-step free response question. And then after you explain how to prepare the solution, they'll have you do some calculations with the solution. Now we're going to add this and form a precipitate or something like that. All right, so this chemist is analyzing the alcohol content in a certain wine. He or she needs 1 liter of an aqueous 0.200 molar potassium dichromate solution. How are we going to make this thing? Okay, well, eventually we're probably going to use about a liter of water, and we're going to throw some potassium chromate in there. It's actually a yellow solid, potassium dichromate. But I don't know how much to use. And if I'm going in the lab, I want to measure my amounts in grams. So let's start with what we have. It's a 0.2 molar solution of potassium dichromate. Cr2O7. Oh, that's a blast from the past. My charges. Potassium is +1. Dichromate -2. We're going to need 2 potassiums. Okay, we know the molarity. We do not know the moles. But we do know the volume. We want 1 liter. Well, that's tricky. So I know the moles. I need 0.2 moles. Okay, I think I can handle that. But again, in the lab, we don't measure in moles. We'd want to measure this in grams. So all we need to do is take that 0.2 moles of potassium dichromate and get that thing out of moles and into grams. The molar mass of 1 mole should be on the periodic table. We just have to add them up. If I add these up on my periodic table, I'm going to say 294.20. And again, we might be using different periodic tables, so if we have varying amounts of decimal spots or anything like that, I mean, as long as we're in the ballpark, we should be good. We're just not going to round unless we really do end up with that off the periodic table we're using. Okay, when I plug this in my calculator, I will leave 3 sig figs because that was the original molarity, 0.200. So this is about 58.8 grams. Potassium dichromate. Excellent. Okay, so we did the hard part. We got the math down. We're going to go in the lab. We're going to measure out 58.8 grams. And then what? There's a little diagram down at the bottom here. This is kind of cute. If I need to explain how to make this solution, I'm going to start with step 1. Measure 58.8. There we go. Grams of the potassium. And this would be a solid. It's kind of a yellowy solid. On electronic balance. Ooh, I should add one thing. Before you do this, wear goggles. Haha. Or whatever safety equipment they list. I'll say safety equipment listed. This is kind of funny. So here's this free response question that's come up actually quite often. They'll give you a list of equipment and they'll say you have all this available in the lab. How are you going to make the solution? If they list like goggles or gloves or anything like that, make that your first step. Step number 1, put on appropriate safety equipment and then list whatever they give you in their equipment list. So if it's goggles, gloves, apron, put that down. There have been times where they've really given you 1 point for just saying like to use safe precautions in the lab. And that means on the flip side, if you didn't say wear goggles or gloves or whatever, they took off 1 point. Brutal, huh? So maybe make a note of that. If there's any safety equipment listed, make that your first step. Then I'd measure out my solid. Step 2, I would take that solid and I would add the solid. Now here again, you'd have to look at what they have given you in their list of equipment. You could use a beaker. We could put the solid in a beaker as long as it was a beaker that holds the proper volume. So here I would need a 1 liter beaker. So if they listed like a 250 milliliter beaker, that would not be appropriate. Or often they'll give you these volumetric flasks. A volumetric flask looks just like this picture. They're okay. You put your solid in the bottom. They only have 1 mark. So, you could get a 500 milliliter volumetric flask. Here I'd want a 1 liter volumetric flask. So it's not something that I would use for measuring. There's only 1 mark on this thing. But they're good for solution making because they've got this bulb on the bottom and you can kind of swirl them real easy and you don't make a mess. So this is a common piece of equipment that they'll probably have on the list. So I'd add the solid first. And then if I wanted to be a perfect little chem kid, in step 3, I would maybe say like add approximately 500 milliliters of distilled water. And then I'd kind of stir or swirl to dissolve that solid. And so that's kind of what they've shown in B. You fill it about halfway, with whatever volume you want. Swirl it up, and then that'll start getting your solid to dissolve nicely. And once you see your solid has started to dissolve, then in step 4, I would add enough distilled water to make 1 liter of solution, 1.00 liters of solution. And that's what they're trying to show in C. Then I'll dilute it to whatever the final volume is. And then we could say, stir it up or swirl so that everything is evenly mixed and perfectly dissolved.